So I view structural equation modeling as being sort of one tool in a very big toolbox, and the more tools that you have, the more things you can do. He has a very big multi-level model hammer that he smashes everything with. So hopefully I can give you something else that is a little more, is different than multi-level modeling. Okay, so to tell you a little bit about what it is or what it does, it probably helps to sort of define structural equation modeling. It's a very large class of models, and I'll sort of go into the details, which might help fix ideas. In general, I think one way to think about it is to divide it up in sort of 3 different components. And one of those components is a structural model, and you may have read some literature or heard about this in terms of path analysis. Sometimes mediation models come up in this sort of guise. And the idea is that it allows you to model relationships among variables that may not be in a standard regression context. So in a standard regression context, you might have one input, or many inputs, but the idea is you have one dependent variable, one outcome that you're trying to predict, and it might look something like that, where X is predicting Y. With a structural model, path analysis, so one of the things that you can do with this is you can actually say, well, my theory says that I've got something else that works in between these relationships. So in a context of looking at like a drug study, for instance, you may say that if you take some drug, that it has some output, maybe it affects your heart disease or something like that, and you might say, well, how does that drug operate? What process does it work through? And you might be able to model that Y variable and say, well, the drug operates through blood flow. It increases blood flow or does something like that. I probably should have picked a different example because I don't really know much about that kind of stuff. But anyway, the idea is that there's some mediating relationship that you can model and test with a structural equation framework. I tend to do things in political psychology, so for me, using structural equation models can be quite useful because I often think about process. So for instance, I had a paper on mass shootings, which is quite depressing. But the idea is that we wanted to look at what the effect of living near a mass shooting was on attitudes toward gun control, and one of the mediating mechanisms might be threat, or how threatened you feel by living close to this. And so we could specify that relationship up there. So that's one component, that structural path analysis type component of structural equation modeling. The second one is this idea of measurement models. So oftentimes in social sciences, I like to joke and say that the hard sciences are considered chemistry, biology, things like that, but realistically the social sciences are the hard sciences because these are hard things to measure. And many times in social sciences, we want to get at things that we can't directly observe, we can't see, so we have to ask questions or we have to try and get at proxies for these things. So, I mentioned in the previous example, perceived threat. Well, how do I know that somebody's feeling threatened? I have to ask them questions about how they might feel. And it's not going to be a perfect measure. I mean, ideally, I would be able to look at Gwilym and say, on a scale from, 0 to 100, he's about a 60 on a threat scale. But I can't do that, I don't know. Maybe he walks around feeling threatened all the time. Maybe he feels pretty relaxed. And I won't know that unless I ask some questions that sort of probe and get at those feelings of threat. I don't know if that was accurate or not, but it was just a guess.
We need to chat, Todd.
So the idea would be that you can use a structural equation framework to get at these measurement models. So I can ask a series of questions in a survey framework and use those to indicate some latent, unobserved construct. So there may be many applications for you, if you're doing your own research, if you have survey, again, I tend to work in survey research, so I think a lot in terms of that, but there may be ways in which you can use these indicator variables to tell you about some latent, unobserved construct. And so that's the second class there. And the idea would be that, you may have heard of it in terms of factor analysis. So there's exploratory and confirmatory. Exploratory is somewhat different. It doesn't necessarily fit nicely in this framework. But confirmatory does. So if you have some idea, some theory, some hypothesis on how the relationships might be, you can use confirmatory factor analysis to tell your audience, or to tell you, how good your measures are at getting at this particular construct. And then the last component can be a combination of those two. So the idea that you can combine structural and measurement components in a full structural equation framework. And then again, that allows you to account for measurement error, So the idea that you've got these measures, they may not be perfect, they're getting at some unobserved construct, and you can then use those to predict some path relationships in a pretty complicated model. And I'll show you some examples of what you might be able to do with it. So it's a pretty flexible technique in that it can allow you to test these very nuanced, interesting theories, which many of us want to do. And oftentimes, standard regression techniques can be limiting in that they don't allow you to do that. So sort of highlighting that, and one of the things I wanted to do is, when you have 20 minutes, is to show you some things that you can do with this technique, maybe highlight some software that might be useful for you, give you some resources that you can go to, and then obviously follow up on a full-day workshop, which we talked about, and I have no idea when it is. And Andy was better about it than putting it in his slide. I couldn't tell you when it is, but I'm sure we'll make the announcement when that happens. So anyway, there are two types of variables that we'd be using in this framework. Observed variables are the ones that you're most familiar with in a standard regression context. These are things that you have direct measures for. You observe these. They can be nominal, continuous, or ordinal variables. The thing, again, that makes structural equation modeling flexible and useful are these latent variables. So these would sort of measure latent, unobserved constructs. We would use indicators, and usually you need to have multiple indicators to measure or test this relationship. And then we assume that they are continuous. So although our measures may not be continuous, so in your survey data, you don't necessarily have to have a continuous measure, but we're going to assume that underlying this, that for Gwilym, there is some underlying construct of threat that goes from low to high, and it's a continuous scale. And if I asked him how threatened he felt on a scale from 0 to 10, it's not a perfect measure, but it sort of gives us an idea of that continuous scale. And then there's some error terms that you can also account for, and I won't necessarily go into the details about it. It's something I would cover if we went into a full-day workshop about this stuff. So some pros and cons, benefits. So one of the benefits, hopefully you've sort of gotten, is that they're very flexible. You can model systems of relationships with multiple dependent variables or mediating variables. You can account for measurement error, the fact that you don't observe these things directly. But there are some downsides to SEMs that you need to be aware of. One is that it requires you, as the researcher, to specify what this whole model might look like. And oftentimes, that can be a very difficult thing. You don't necessarily know whether one approach fits better than the other, and you can use some fit statistics to try and do that, but in reality, it can be sometimes difficult to say, well, I've got a full survey. If you think about, for instance, the British election study, there are hundreds of variables. How do I know which variables to include in there? You need to have some theory that helps you. It's not an exploratory technique, I guess is what I'm trying to say. It does require a decent sample size. Now, large in the days of big data might be different for some people than to others, but it is the estimation techniques use maximum likelihood, so they are asymptotic properties, basically meaning that you have to have a sample size large enough to get at reliable estimates. And realistically speaking, if you've got a survey size of say 200 or a sample size of 200 or more, you're usually okay, depending on how complicated your model is going to be. And again, we would go into details about that kind of thing in a one-day workshop. The other thing to note is, although we're specifying various paths, and we might say that we believe this causes that, and we have arrows going all over the place, it is still a correlational technique. And really the only way to get at causality is to have a randomized controlled trial or an experiment to test those causal relationships. So although we might use this to test mediation, realistically, the best way to test mediation is with an experiment where you can manipulate things and show that that's the only causal difference. That being said, researchers use it all the time to test these relationships, and it's oftentimes better than not doing it at all if it's part of your theory. Okay, so in terms of, one of the next things I wanted to get into is just sort of how is it different than standard regression techniques? What makes structural equation modeling different? Why isn't this normally taught when you're taking graduate classes or what have you? And so one of the things, or one of the ways it's different, is that the basic statistic for SEMs are covariances. And covariances are just unstandardized correlations. usually, and it depends on what we're doing, usually you're not looking at means. And so if you think about regression analysis, you're looking at mean differences. For structural equation modeling, you're looking at covariances. And I'll show you in a second that it's very similar to regression, but it's not quite the same thing. So you do need to note that difference. If you care about the formula, there's the formula for how covariance is calculated. And if you've seen a regression formula, you'll notice that it's very similar. The denominator's slightly different. So what we're trying to do is we're trying to understand the pattern of relationships, the pattern of covariances in the model, and trying to explain as much variation as possible. So one of the things that you'll get when you get your estimates is you'll get sort of some relationships among the variables, and then you'll get some fit statistics to tell you, well, how good does this model fit the data? And we're trying to explain as much variation as possible. And again, that's stuff we would go into on a one-day workshop. Again, I mentioned, how does it differ from regression? A standard regression coefficient, a slope coefficient, some of the stuff that Andy was talking about in his last slide, that's sort of how you calculate it. It's related to correlation, but it's slightly different. And so we're going to be working with covariances for the most part. And if you have no idea what I'm talking about, we would go over this stuff in a one-day workshop. So don't feel bad if this isn't familiar to you. All right, so how do you do an SEM? Like, what are the steps? So I'll walk through this, and then the next thing we'll do is I'll just show you some examples and show you some software that I use that I find useful. So, the first bit is use theory to specify a model. So that's not very different than what you'd be doing in a standard regression context. You'd estimate this model using software, and again, I'll sort of highlight some various software that you could use. And then the next step would be evaluating model fit. So oftentimes when you're conducting a standard regression, you might sort of do steps 1 through 3 and then say, okay, I'm done, and then that's it. Or sometimes maybe it's doing 1 through 3 lots of times, but usually it's sort of, you go 1 through 3 and then you're done. In our case, we're going to be using the model fit to give us some information, and in all the years that I've been using structural equation models, you never get to that third step and say, okay, wow, I'm just so smart, and the theory is great, the literature is great, I'm done. Usually you have to go back and say, okay, the model fits okay, it doesn't fit great, so why isn't it fitting well, what am I missing, and then respecify the model, using theory, of course. So you use theory to respecify it in a way, and then again, reevaluate how well that fits the data. Do this as many times as possible, as needed, to get a good fitting model, and then you can sort of worry about interpreting the results, which can be difficult at times given how complicated the models can be. But the idea is you sort of walk through these 3 steps and then repeat them as many times as needed to get the model that fits the data best, and then you can interpret what those estimates mean. So in terms of software, there's a lot of different software that's out there that can do structural equation modeling. In the past I've used M+ a lot. More recently I use R. It's a very flexible package, and I'll talk about which specific packages do structural equation modeling that I think are pretty good. But you can use various ones. Stata is getting better at these things. Oftentimes some of the limitation in the other packages is the types of inputs that you can put in. So, for instance, SPSS sometimes won't allow you to use dependent variables that are not continuous, and that can be problematic. Whereas R, or some of the ones that might be a little bit more cutting edge, allow you to use binary dependent variables, ordered dependent variables, those sorts of things that oftentimes as social scientists we encounter more than just continuous variables. I don't know, usually I don't have very many continuous variables in my research. I ask survey questions, it's like a 1 to 4 scale or 1 to 5 scale, 1 to 7. I don't usually have a lot of continuous measures in my data. So using a software package that allows me to model those things is helpful. So which one do I tend to use? And this is sort of what I would teach in the workshop, would be a package called Lavon using R. So R is a statistical software. It's free. Free as in beer, which is good. we all like beer. It generally has sort of the cutting edge methods introduced to it. So oftentimes, statisticians are coming up with new methods and new models, and they are first introducing them to R. Then they picked up by M+ or by Stata. And then many years later, SPSS, if ever. I'm not a huge fan of SPSS, but I understand that many of you use it and understand it and work with it. What I would say is that although it looks a little scary, when I first started using R, one of the reasons why I needed to use it was because my data was composed in such a way that I could only use R. I couldn't use SPSS to do the analysis. So I thought, okay, I'll need to sit down and do some stuff. And you write a few lines of code, and it's like, okay, so I can do that. I definitely can't use R very well, but I can do my analysis. And then over the years, you get better at doing other things. So I would say that, it looks scary, but it's not that bad. And after the one-day workshop, many of the students, I should say all of the students, can do the analysis that we cover using R and feeling more comfortable with it. So I put up an example up here just to sort of show you that that's all of the coding that's required to do this full structural equation model where you have latent variables. So all of the round circle things are the latent variables. All of the squares are the observed variables, and you can model something pretty complicated with a few lines of code and get a pretty detailed analysis out of it. So just to sort of cover what you might see in R, so if you were doing a simple regression analysis, so here you have 4 independent variables and 1 dependent variable. So the first step would be sort of import your data, fit your model, and then get some summary statistics. Get your output. Lavaan is very similar to that. So you might get some regression output that looks like this. This is what comes out of R. It's pretty standard to what you'd see in Stata, SPSS, or other packages that you may have used. Using Lavaan, again, you can do a simple regression analysis the exact same way. The code is slightly different, but it's very similar. So you import your data, specify the model, then ask for some summary output, and you'll get something that looks like this. So you'll notice that the estimator is maximum likelihood, but the estimates, the coefficients that come out of the model, are exactly the same as you'd get from a standard regression approach. Again, this is because it's a simple model that we did. But you can also specify other things. So, one of the things that people sometimes ask me is, well, what happens if I have multiple dependent variables? I have multiple outcomes that I want to look at. So sometimes people create scales with those things. Other times they may be distinct, and you may not want to combine them. You may want to model them in a framework like this. So you could look at multiple dependent variables, which can be very useful. And again, that model is just a single, maybe 2 lines of code, but it's not much more complicated than specifying a standard regression in R. If you want to do mediation, so using a structural equation approach is a very good way of doing mediation if you have correlational data, which many people have. So I know that there are other approaches that you can do where you regress your mediator on your predictor, and then you regress your output on your outcome on your mediator, and you can look at those. You can actually just specify this in this path analysis framework and get the effect, the direct effect and indirect effects. And we would talk about that in the workshop. You can specify more complicated paths. So in this case, we don't just have a single path, we have multiple paths that you can look at. And again, the code is very similar, very simple. You're adding on a few extra variables, but it's not much more complicated than previous examples. Confirmatory factor analysis. So you can do something like that, where you've got 3, in this case, we have 3 latent variables, visual ability, textual ability, so probably reading comprehension and how quickly they read. And we have a number of different indicators. Or a complete structural and measurement model that looks something like this, and this is the example that I showed before. So again, the idea isn't necessarily to scare you or to make you think that this is overly complicated. It might look like that, but if you spend a little bit of time in the workshop or going through some of these resources, you'll see that it's quite flexible, and it's pretty powerful given that you don't have to specify tons and tons of coding. So the last thing I wanted to do is just sort of go through one example just to maybe fix ideas. I'll give you some books that I use as resources, and then we'll sort of wrap up for today. So for an example, might be interested in social welfare spending, sort of what predicts preferences to social welfare spending or attitudes toward government. There might be a number of predictors, so standard literature might say, well, ideology or party affiliation might affect how much you want to support the welfare state. Maybe your personal experiences, how your personal income is, low or high, whether you're part of certain generations which experience, say, the financial crisis or World War II or what have you. Other literature shows that people might look at the beneficiaries and might say, well, who's getting the money? Are they deserving or not? I want to help some people but not others. And then there's another literature that sort of looks at pro-social orientations, like your humanitarian values, how much you value helping others, how much empathy you have toward others, how much you can put yourself in somebody else's shoes. So, without going into all the gory details of it, just to give you a sense for how that might work, there's some election data out there that looks at this sort of stuff, that has a number of different measures from completed surveys, from a nationally representative survey. We've got items for a number of these different things that we just looked at, and we'll see how we can model that. So we might specify a path relationship that looks something like this, where we say, okay, well, the standard literature might only look at sort of these demographic predictors of the welfare state. So your party affiliation, your ideology, what have you. And then we might add on humanitarian values and say, well, how much do you value helping others? And then we can also include some of those pro-social orientations like empathy and see how that plays out in predicting spending or attitudes towards spending on social welfare. So we could fit the model, get some fit statistics. This particular model fit quite well, and again, that's the kind of thing that we look at. There are a number of different fit statistics that are common in the literature that we would discuss. And then, because of each of these things are latent constructs, we have a number of indicators in the survey that sort of that are used to indicate these particular constructs. So we can say that empathy is predicting your humanitarian values, which is then predicting your support for social spending on social welfare programs, controlling for a number of demographic things. So anyway, the idea again is that you could specify a pretty complicated relationship. So this is all the arrows and everything going here. That's the code that used to produce the entire output for this particular paper. So a few lines of code, that entire output for a published paper is it's not too bad, right? It's something that can be done, and again I will show you how to do that if I'm doing my job properly.
Don't just copy that, though.
Yeah. In terms of resources, oftentimes people ask me what resources are available. There are a ton of resources available on the internet, on the web. In particular, the Lavon package has pretty good support and tutorials. So if you go onto the website for Lavon, you'll see that he provides a number of different examples and sort of walks through how to interpret the outputs and what have you. But there are also some books that are useful. There are many different ones out there. I think these ones are pretty good because they combine a nice, they have a nice combination of practical, hands-on, how to do things, also with theory. And the books aren't entirely in Greek letters, which is usually helpful. Sometimes people recommend books to me. I know my econometrics textbook when I was a graduate student was maybe the Wooldridge one, and it was all like Greek letters, and I thought, I don't really understand any of this, and this isn't very helpful for me. So these books actually use words to explain concepts, and they do have some formulas, but they also provide code to show you how to do things and how to interpret things properly. So I think they might be somewhat useful for you. And I think that's everything I have for today.